This is your lecture number 3 for strength of materials. Let's go starting from composite bars. You have composite bars. Let's say you have a bar say it's a hollow tube made up of one material, and inside that you fit another material. We say that as a rod. Say any rod you fitted inside of another material. This one. So this is your material 2, this is your material 1. Now you are fixing, you're keeping the joint as rigid by a rigid plate. Say you have connected these two by a rigid plate. So by your uh, composite action means say now you apply any force P. So you apply any force P, it would since material is your deformable material, they would either compress or either elongate or get compressed. So but for the composite action we say your delta relative is equals to 0. That is the change in length of material 1, change in length of material 1 of material 1 and 2 are same. That's your composite action. Say you are having concrete and steel in the RCC, you say that as a composite action. So let's say you are applying a force P. Now we can say that let's say your material 1 takes load P1 and material 2 takes load P2. Then the total load goes to P. Say this is reacting with some force P and your material 2 is reacting with some force P2, and we do summation of forces in X goes to 0. Now but the condition is like you are having two unknowns, force P1 and force P2, but your equilibrium static condition is your only one, that summation fx goes to 0. So for the second condition we can have this compatibility condition. Then we can say delta relative equals to 0. So the amount of change in length in 1 and 2 are the same. So we can see that for the material 1 it's actually, let's say your material 2 takes load P2, and length is same for the two materials, PL, material 2 area, and material 2 E2, and plus you have we can say the amount of deformation in this one has to be equals to amount of deformation in P. I can say P, because of force P1, material 1 will be also having the same amount of displacement or this change in length. So we can write P1 L upon A1 P1. So from this compatibility condition we can get relation between P2 and P1, and we can have the unknowns. We can get the unknowns P1 and P2. Reactions are also two. So let's say this one is your this one is your delta 2, that's equals to delta 1. Now if we substitute the value of say P1 in the equation 1, what we can get? See, we can write as say P2 equals P1, P2 equals P1, and you have A2 E2. P2 equals P1, and you have A2 E2 by A1 E1. Now substituting the value of P2 in the equation 1, we can have P1 plus P1 A2 E2 upon A1 E1 equals P. Now we can simplify. We can say P1 A1 E1 plus A2 E2 by A1 plus A1 E1 equals P. So your force in the material 1 in terms of total load equals this one, A1 E1 by A1 E1 plus A2 E2. So it's like a weighted average of AE. So we can say PI goes to P into AI EI by summation of all AI EI. So similarly, P2 we can write as P A2 E2 upon A1 E1 plus A2 E2. Now uh, now say the total deformation, since both materials having composite action, we say that delta 1 equals delta 2 equals total delta. That's equals to any load. Take any load. We can say taking any load. Let's say P1 L upon A1 E1. If we substitute the value of P1 here, we say that P1 equals P A1 E1 upon summation A1 E1 into your value of L by A1 E1. So your delta I equals P by PL by summation of AI EI. So any delta, or because all the deltas are same, we can say that if you want to say any delta, or you can say delta 2, delta total, delta 1, that are all equals to PL by summation of AI EI. So now let's say if you want to substitute or replace, if you want to replace the two composite material, if you want to replace the composite material by a single material, then and keeping the for the we can replace the material for same amount of deformation, for same delta, same amount of area. Area equals A1 plus A2, and same amount of load and the same amount of length. We can get the equivalent modulus, Young's modulus of elasticity. So for that we can replace the total composite by a single material of length L, area A, and and the force is P, and the force is P. Deformation is also same. So we can write as the change is only the E equivalent. So we can say by 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 the condition that delta equivalent equals delta of the composite, we can say delta equivalent we can write as P L upon area was A1 plus A2 and E was your E equivalent, and delta composite was your PL upon summation PL upon summation AI EI. So we can have E equivalent equals equals summation AI EI. Yeah, summation AI EI by summation AI. This is your E equivalent. Okay. Now write new topic. We can say it's your problem involving temperature change. Let's say you have a bar. Okay, you have a bar resting somewhere. You have a bar of length L. This is your bar of length L, and say your temperature rise by T degree, or we can say delta T. For easy analysis, I write it as T. Actually, it is delta T, change in temperature. Let's say temperature rise by T degrees. So your material, since material is having coefficient of thermal expansion, say alpha, we can have the expansion of the material. Since there is no restraint applied on the body against the temperature change, so your material is going to expand because of temperature rise. Say the amount of deformation because of temperature rise, that's proportional to the length of the bar itself, and deformation of the bar is also proportional to the increase of temperature. So we can have delta equals alpha. This one is your proportionality limit, and alpha is your coefficient of thermal expansion. This is your constant proportionality. We can write alpha LT, control alt. That's how I remember this. Delta is your alpha LT. So but here the since this is your free expansion, since this is your free expansion, here the stresses, thermal stresses developed are equals to how much? Equals to 0. Why so? Let's say we don't accept this thermal stress is 0. Since there is deformation, there might have been stresses developed. Since it is free, let's say its free body diagram looks like so it's expanding in your longitudinal direction along the line. So say it has deformed by delta. We can say, let's take the free body diagram. Say it was your final length. Let's cut any section, say anywhere. Say it's your section. You cut the section, you check it, what's happening inside. This is your section. Let's say you assumed you want to say that the forces are acting somewhere. Let's take uh, uh, for the elongation to prevent, say say the stress or load is acting in this direction. Okay, and and for the internal you have to apply this opposite direction p. Okay, okay. Let's take here also p. No, we can write it, sorry, we can write it as reverse. We can write it uh, in the opposite way. We want to check, we want to say that we want to say the internal forces have been developed. External force is not there because there is no support to balance the system. So you're in the x direction, there's no one to prevent the stresses happen, this elongation to not happen. So we let's say we say the internal forces has been developed. We say the force internal has been developed, but here there is no support. So since there is no support, here the opposite reaction should be zero. So so it doesn't make sense. If it is zero, that means P internal has to be zero. So your sigma has to be zero. So आपका ये expand हो रहा है तो material should say ये expand क्यों हो रहा है? There should be some internal resisting force trying to prevent the expansion of the material. So by the free body diagram, let's say there was internal force, but when we do the free body diagram analysis, we say that there is no reaction in this direction, so we can say P internal is not there. So your stresses are not happening on the cross section. So let's take now your indeterminate structure, say a beam or a bar between two fixed supports. Now it's a material of length L and coefficient of thermal expansion alpha. You raised the temperature by T degrees Celsius. T degrees Celsius you have increased. T degrees Celsius you have increased. Now calculate the thermal stresses. We want to say if there are any thermal stresses. So we say since your SOM strength of material is the steady under elastic limit, we say load is under elastic limits, that your rod was 100 mm, uska 0.1 mm elongation is your strength of material. That's your strength of material total. So since it is in elastic limit, we can have the effects. We can study the effects, individually by using the concept of superposition theorem. We can superimpose the two effects uh, to ensure compatibility condition. To ensure the compatibility condition, we can apply the superposition theorem in this way. Say, let's take the first case that there was no supports and the material is freely expanding, free expansion. This is your number one. Removing the supports, so we can say this is your material alpha L and temperature has been increased, so your deformation equals this much, delta equals alpha LT. We can write it as this way, alpha LT, alpha LT. So this is your material of length L. It has been expanded because of thermal this temperature increase. So your material has been expanded by alpha LT. So now the to study the effect of your reactions, there is no, we can say there is no internal, there is no external force. So we can write summation of Fx goes to 0. Let's take now the free body diagram. We say that assuming the reaction to be opposing the this change in length, we can say this is your reaction at support A and reaction here at support B. So we can say reaction A has to be equals to reaction B. Say that's equal to some restraint R, because the summation Fx goes to 0. So your support reactions are same. Now this is opposing the expansion. We can say now your effect number 2 is the redundant effect. You can write effect of redundant. So your this is your R and this is your R. So it will let's say, sorry, we can keep it this way also, or it doesn't, because your deformation is not smaller. Or we can say, let's take now the case when it has already deformed to this amount delta. Say it's your new length. Now take that initial one, because your sum is like after the expansion L dash is almost equal to L. Okay, so it's your restraint R, length is L. We can say the effect of yeah, why I removed the part, because we are using the superposition theorem. So one of the assumption was, second assumption was that the effect of loading 2 should not affect the deformations of loading 1, or the effect of on the loading effect of, because of the loading 2 should not be affected by the deformations caused by the because of loading 1. So we can have from the second condition, we can say your deformation against, this was your deformation in this direction. So in this direction your deformation is R L upon A E, area cross section. So by the compatibility condition, we can say total change in length equals to 0, because this support and this support, they won't allow any deformation to happen. So we can say delta total equals to 0. This is your compatibility condition. So we can write as RL upon AE. It's your compressive force. Your deformation is negative, plus the first one was your change in length was alpha LT goes to 0. If we compute the value of, say, R by A is, this is your R and this is your area cross section, and this is your R. So we can say sigma thermal, or we can say sigma T. This is your thermal stress, L by E, and we can say equals alpha LT. So your sigma thermal equals EAT, EAT. Say this way, E alpha T. So your thermal stresses have been developed here that are equal to EAT, E alpha T. So now the next part is your Next part is your taking the next part, say temperature change, with yielding supports. Temperature change with yielding of supports also. Say the material. Say this was your structure. This one, the length was L. So after increasing the temperature to T degrees Celsius, or we can say changing the temperature by delta T degrees Celsius, we have the material has been expanded, and say the supports are also yielding by an amount of delta yielding, delta y. So we can say for the free expansion to happen, say your free expansion, we can write it this way. Say your material was there, now it has expanded by alpha LT. This is your alpha LT. This is your delta because of temperature change. So now the second one is your because supports are yielding, say the stresses would develop only after delta y, after material, we can say after the material, this one bar, or we can say after the material L have been expanded by delta yield. Say that's delta y of the support. This is the summation of the supports, delta y. We can say since when the if the support is also moving, say material support is going up to this point now because of the yielding. So this way here, say this is your delta yielding. The amount of stresses will be developed for this part only because this have been prevented, delta prevented. Say this one, let's take this way. Now the material has been expanded to L plus ALT. Then say the reactions are this way, R L by AE. So R is there, but the material has been expanded. Now there was yielding of the material. We can say, see, since from this part to this part it was your alpha LT, okay, and for this part this is your yielding of the support, and this part was your alpha LT. So the resistance is developed only after the material has yielded delta y. Then after that the stresses would be developed for this length difference of these two. So we can have the compatibility condition that the RL by AE is your compressive plus delta yield equals alpha LT. Then we can say your stress sigma thermal L by AE equals alpha LT minus delta y, and sorry, this is your sigma L by E. We can say your sigma thermal, keeping the sign, removing the sign for now, say say your sigma thermal, uh, yeah, sigma thermal equals E by L alpha LT minus delta Y. So we can say this is your E by L. This is your delta free minus delta yield. So your sigma thermal is equals to E by L delta free minus delta yield. So we can say your stress would be developed only for the part for which delta is prevented. Delta prevented. The negative was here, meaning the stresses were compressive, that the negative which I removed. So you can keep it or not. For the equation we say that just keep it positive. So this is your equation for the yielding of supports also. So now we have the composite. We have the composite. Let's go to the top. Let's go to the next one. That's your composite bar. Composite bar and temperature case. Temperature change case. So we have the composite action and temperature is also varying. Say for simplified analysis, we don't make now this one this way, the two bed rod. We can keep them like place it one after the another. Say this one, this material, and next one is your this one. Length is same. Composite action we know delta relative is equals to 0. Now say the material has been expanded by so it is your length L. Say material 1 is having say material 1 is having E1. Let's take the case of copper and steel. Say for the copper you have alpha copper equals to 18 into 10 to the power minus 6 per degree Celsius, and for the steel you have 12 into 10 to the power minus 6 per degree Celsius. The more alpha means more sensitive. If you are having more sensitive, if you are more sensitive, that means you are more prone to change in the length quickly. So you are more sensitive to temperature change. So let's say this one is your copper ECU alpha CU, and this one is your alpha ES steel alpha steel. Okay, now say we can superimpose the effects. Let's take the study for the copper. Since alpha for the copper is more, we say for the free expansion of the copper we have free expansion of copper, L free of copper equals alpha copper L T. Temperature rise, say temperature was rise by T degrees Celsius. So your free expansion of copper was alpha copper LT. So let's say it has been reached to this point. This is your alpha CLT. But the now the free expansion of steel is alpha steel LT. Since your alpha copper is greater than alpha steel, so your free expansion of copper is more than that of your steel. So but the composite action says delta should be same for the two members. So we can say, let's say steel has been yielded to this part. Now, but it's not ensuring the this composite action. There has to be some, say this one has to reach somewhere here, and this one has to be have to reach somewhere here, in order that the final displacement of the two material is same. Say this one is your delta final of the composite. So here there's no external force, so F external summation of Fx goes to 0. uh, there's no external force, so if you have to get this steel to this place, you have to extend it. So here have to be applied some force of tensile force of P. So force in the we can say force in the steel in this direction, and here if the copper has expanded more, it had to be compressed by some delta, in order that the overall delta final of the composite equals is the same. So that, so for that, here has to be some force, compressive force C in the copper. We can say force in the steel in this direction, plus force in the copper in this direction have to be equals to 0. So your force 1, so force in the steel equals force in the copper. So this one is your first equilibrium condition. So we can say force is your stress in the steel into area cross section of the steel bar, and this one is your sigma copper, area copper, keeping it as equation 1. So and the second one, we have to get the uh, stresses in the two materials. This is our here unknowns, to get the stress in the copper bar and the stresses in the steel bar. So for that, we have equation 1. We got the equation 1. Second equation we can get from the composite action compatibility. We can say by the compatibility condition, we can write here, by the compatibility condition, compatibility condition says of composite action delta, the amount of deformation in copper wire have to be equals to delta copper net have to be equals to delta steel net. So deformation in copper net have to be equals to alpha copper LT. It has expanded, and you are preventing by an amount of, say the force, say that now the force is finally, since the force is same, let's take the force as, say, P, and we can prevent the deformation. We have PL upon A, area copper, E copper equals to, yeah, it is negative actually. This one is your negative, P is your compressive. So PL by AE, and for the steel we have alpha steel LT plus, and for the steel the P is trying to elongate it, so it is your positive value. We have PL by area steel, E steel. Now we can write the P by A in terms of stress. We say alpha C, and keeping the alphas in the one direction, in the one side of the equation, we can say your your P by area cross section is stress in steel, stress in copper, and stress in copper, and you have EC, and length is L plus sigma steel. This one, this one is your sigma steel. This one is also negative. This one is also negative by shifting. Sigma S is say sigma S L upon ES equals alpha steel LT plus alpha, alpha copper LT. Yeah, negative, we can say. Alpha S is your positive, and alpha C is your negative. Alpha C minus alpha C LT. So we can have some terms common. We can say sigma C by EC plus sigma S by ES equals alpha copper minus alpha steel into length, no length gets cancelled, and you have only temperature T. So you got this equation. Yeah, so we had two equations, and we were having two unknowns of stresses. So these are your two equations. So this is the case now for the temperature rise. Now second case is your temperature fall. Let's say the temperature decreases by delta T. Temperature fall, delta T decrease, T degrees Celsius decrease. Say that this is your copper, this is your steel, alpha copper, alpha steel, E copper, E steel. So say since the alpha copper is greater than alpha steel, so the change in length of the copper would be more than change in length of the steel for in the free expansion case. Now the temperature is decreasing, that means more amount of decrease would be in the copper than in the steel. So we can have this way. We can remove now. We can shift to this part here. Say this is your copper, this is your steel. Now alpha copper is more, so your say the material copper has been shortened by amount of alpha copper LT. It has been shortened from this point, say it has reached to this part. So this part is your alpha C copper, alpha copper LT, and say the steel has also shortened by amount of this part. So this is your alpha steel LT, but the composite action, for the composite action to happen, the relative displacement have to be 0. So final change in length of the composite bar have to be same in both the bars. So let's say this is your final location of the bar. So since the copper has been shortened by this amount up to this amount, but final value is this one, so on the copper bar there has to be some force, compressive force, and because of that compressive force, say this is your cross section, here the stresses developed are sigma C, and in the bar steel, it has shortened by less amount than the final displacement of the steel bar. So there has to be some tensile force acting on the steel bar. So we can say this is acting your sigma C, sigma S. So this sigma C and sigma S we are writing based on force equilibrium we have studied in the temperature rise case, that summation fx goes to 0. Then we write force in copper equals force in steel, sigma C area copper, and sigma S AS. This is your equation 1, and we can have equation 2 by the composite action and this compatibility condition. You can write compatibility condition. Compatibility condition says that your delta net in copper have to be equals to delta net in steel. Writing the delta net in the copper is it has shortened by alpha CLT. We can write it as minus, say it has decreased the length, but you are applying a this tensile force of sigma tensile stress of sigma C L by E copper equals say the steel has been yielded by minus alpha SLT plus and the tensile force and the tensile force, yeah, it's tensile force sigma S L by ES. If it is tensile stress, so it has to be negative. It was negative actually. It is compressing the material to this final location. So sigma C is your negative compressive. So we can have the same equation. After simplifying, we get same result irrespective of whether temperature is increasing or decreasing. We can have sigma C by EC plus sigma S by ES equals alpha copper minus alpha steel into temperature change. Temperature change has to be here magnitude, no sign. We have already encountered the negative sign in the derivation. In this, when you simplify the equation, you would get this value. The negative we have already substituted here now, this one. So keep the value of T as by how much you are decreasing the temperature, not minus times that. So this one. Now we can say, we can have the conclusion. It can be a like 1 mark question. Sometimes we can say it is a conclusion. Say temperature rise case. Say alpha 1 is greater than alpha 2. It is composite action. Alpha 1 is greater than alpha 2. That means material, we can write here materials. We can write here materials, material 1, material 2. And for the temperature decrease, we have alpha 1 greater than alpha 2. We can get the materials. So we would say, what should be the nature of the force or stress in material 1 and material 2? Now, so say your temperature rises, so this expands, material 1 will expand more, so on that compressive force have to be developed. So your material 1 is experiencing compressive stresses, and the material 2 will be having tensile stresses. And in the temperature decrease case, alpha 1 is more. So if alpha 1 is more, it's shortened by more amount of delta. So final delta has to be less than that. So you have to actually, it's expanding, it's contracting more. So you have to kind of we can say material for which alpha increases, we have to apply tensile force on that, tensile stress. And in this one, you have compressive. Actually, we write here negative. It was actually wrong. We can have this one, and we can have this one. See, for the alpha copper is more, alpha is more for copper, so it has shortened by more amount of deformation. But the net final deformation have to be equals to this one. This have to be equals, this one is your final deformation, delta final. So if it was short, say it was your shortened length of the copper, so this part have to be elongated, this part have to be elongated. That can be only possible if the stress is tensile. So this stress was your tensile, this was your tensile stress, and this one is your negative compressive. So this is the conclusion. Compressive forces or stresses, you can say. Now we have series connection with ends supported. Okay, right. Series connection with ends supported. Say you have two bars in series. Remove this one. You have two bars in series. Say bar 1 and bar 2. Between two fixed supports. So this is your series connection. So you're now you have to do what? You have to say change the temperature by delta T. If the temperature is changed by delta T and the external force is also not acting there, we can say, let's write summation Fx goes to 0. We can have, say, we can do the free body diagram. We can have this one. Among the supports, we can say this is your, say this is your reaction R, reaction 1, this one is your reaction 2. We can say reaction 1 have to be equals to reaction 2. Say the reaction is R. Second one is your, we have two unknowns here, reaction 1 and reaction 2. Now we have one unknown, like we know reaction 1 is equal to reaction 2 equals restraint R, but what's the value of R? How can we get the value of R? So for that we have compatibility condition. Say the material 1 have been expanded by, say its alpha is alpha 1 and length 1. Here it's alpha 2 and length 2. So we can say the temperature change, say temperature has been increased, temperature rises. If the temperature rises, your material will expand. So your material would expand, say material will expand. We can say this one would go by this amount. This is alpha 1, this is L1 plus the amount of increase is alpha 1 L1T, and in the material 2 it has expanded, so your length, final length is L2 plus alpha 2 L2T. So now by the compatibility condition, we have to prevent this change between the fixed supports. So both of these both of these deformations are trying to increase the material, but both here on the both sides of the this member, there are fixed supports. So from each side there would be compressive forces developed. So from each side compressive force would be developed. Here is R, same amount of R, here is R. So if we do the effect of redundant support, we can say the the R is trying to compress the material by, say, this is your compressive force R. We can say R L1 by A area A1 E1 plus, and because of this one, for this part we can say, because for this part we can say minus R L2 by area 2 E2. So by the by the compatibility condition, now we say, taking it as delta restraint resistance. So your compatibility condition is delta resistance plus delta because of free expansion equals to 0 between the two fixed supports. So delta resistance is your, we can write as, say, this is your minus, but R by A is your stress, so it becomes sigma 1 L1 by E1 plus minus sigma 2 L2 by E2 equals equals to delta free, or we can say plus delta free. Delta free is your plus delta free is your alpha 1 L1T plus alpha 2 L2T. So this is your equation. If we simplify it one step more, we say sigma 1 L1 by E1 plus sigma 2 L2 by E2 equals alpha 1 L1T plus alpha 2 L2T. Now let's say the material, say the support. Now let's say the supports yield by delta y. If the supports also yield by delta y, so the stresses would be developed only for the part which is being prevented. So we can say sigma 1 L1 by E1 plus sigma 2 L2 by E2 equals alpha 1 L1 T plus alpha 2 L2 T. This was your delta free, minus you had to subtract the delta yield of the delta yield of the that support, delta free minus delta yield. So this is your equation. Now take the we can take, yeah, actually we can say in this case, series connection case, each bar is experiencing a compressive force. So in the both the bars both are having compression. When your temperature is increased, and if the temperature we are decreasing, then the stresses have to be tensile in the both bars. Now let's take a problem. Say your problem is you have a copper bar For L by 2 length, its area cross section is 50 mm square, and for your next L by 2 you have 100 mm square. This is your copper, and the steel bar is also there, area of 50 mm square. This is your steel. These two are acting as a composite, so we have they connected them between two rigid plates. So this one, these are your two rigid plates. These are your rigid plates to maintain composite action. Say that these are rigid plates. That does not mean that they won't allow the material to expand. They would expand or contract by some amount that is same for the two materials. If it was rigid support, there would have been net displacement of 0 for the two materials. For the rigid plates, we might have some displacement. So we can say here we can say external. We have to get the sigma copper and sigma steel. For that, we need to get the forces. Say the summation of forces goes to 0 uh, now, but we don't know the forces initially. Let's do the free expansion case first. Now your temperature temperature rises by 30 degrees Celsius. You have to get the stresses in the rods. You have alpha copper. So alpha copper is written here 1.5 10 to the power minus 6 10 to the power minus 5 per degree Celsius. And alpha steel is your 1.2 10 to the power minus 5 per degree Celsius, and your modulus of elasticity of the steel is your 2 into 10 to the power 5 megapascal. Megapascal. And for the copper, it is your 10 to the power 5 megapascal. So firstly, we can do the free expansion case. If we do the free expansion case, we say how much expansion of the, say, firstly check here. See, the free expansion of material is alpha LT. It does not depend on the cross sectional area. So material is same, it's L1, and material L2 material is same. So your free expansion is L1 plus L2 alpha T. Alpha is same. It is not dependent on the cross section properties. So for the copper, you have delta copper, we can say delta, we can write it as free expansion, delta copper equals L by 2 plus L by 2, L by 2 plus L by 2, and alpha of copper is your 1.5, 10 to the power 1.5 into 10 to the power minus 5 per degree Celsius into temperature rise by 30 degrees Celsius. So your expansion becomes equal to, say L is not known to us, say some delta copper. Now for the steel, delta steel is equals to L, the length is same L, and alpha steel is your alpha of steel, that is 1.2, 10 to the power minus 5 into change in temperature is your 30 degrees Celsius. So here the only difference is in terms of alpha. Here alpha copper is greater than alpha steel, but for the composite action the materials have to be deformed by same amount. So if we write it, if we say this one is your this is your copper bar, say the net of these 1 and 2, that is equals to, say I'm writing as this much, that is alpha copper LT. And for the steel bar, you are having steel bar, this is your copper, this is your steel, and it has expanded by this much, alpha steel LT. Alpha copper is more, so your free expansion for copper is more, but for the composite action the net relative displacement between the two bars have to be 0, so they will adjust to somewhere in between the two free expansions. So for the steel, we say apply tensile force on the steel, and in the copper bar you have to apply compressive force. From this position you have to reach it to here, so your force in the copper is compressive force. By the force equilibrium, we say summation fx goes to 0. We can say copper sigma copper C, force in the copper is Cc have to be equals to Ts. Say that the force is R. So your unknown is only that reaction R. Say you are applying compressive force here R, here is also R, but in this material it has to be tensile force, of equal to R. It has to be R. So we can say by the strain, by the compatibility condition, we can write compatibility condition says delta net of copper equals delta net of steel. Delta of copper, delta free of copper was alpha copper LT, and on the copper you have applied compressive force, so it has minus compressive stress on the copper, length of the copper by E of copper, and that has to be equals to free expansion of steel alpha S LT plus, and on the steel you are applying tensile force, so it's tensile stress positive, sigma S L by ES. So after simplifying, we can have See, your length is also unknown. Your length is also unknown. And here length gets cancelled. Length gets cancelled. So we can say alpha copper temperature plus, keeping this alphas in one side, we can say alpha steel T equals sigma S by ES plus sigma C by EC. So the equation becomes sigma C by EC plus sigma S by ES equals alpha C minus alpha steel into temperature. And your first equation was that force 1 equals to force 2 equals to P, that we have represented by R. We said that sigma copper into area copper have to be equal to sigma steel area steel. But this condition, if we see, this is not valid truly if we see the copper bar. For the first part, your area is 1, area 1, and for the next part, area is changing. So you can't say this way. Here area of the copper is what? Which one? Area 1 or area 2? So we can't write in terms of stress. So we have to convert the stress in terms of the load itself. If we get the load, we can get the value of stresses. So your question is actually stresses in copper in the first part, sigma C1 and sigma C2. This one is your sigma C1, sigma C2. Stresses would be different because area cross section is different. So we can convert the stress in terms of load. Say sigma C equals to P, or we can say reaction R, reaction by area cross section. Oh, here is the problem actually. Yeah, we have a problem in the result actually. Since the material copper have different cross section for different lengths, we need to do the separate calculations. We need to adjust to the equation. This one is okay. For the steel, it's all okay. This is this way, and you need to remove this part. See, this was your free expansion for the copper, and plus there was tensile compressive force acting on the steel bar, on the copper bar here. Tensile force was compressive force was being developed. Compressive force on the copper bar. So we can say reaction L by 2 area 1 of the bar. Let's say area 1 of the bar was 50 mm square. Area 1 of the bar was this one, area 1 that we have already known, that is 50 mm square, and area 2 we have 100 mm square. So we can say, and both in the both if you do free body diagram for this, we have reaction R here to be reaction R, it is compressive, and in this part is negative, it would be also negative. So we would say for the first length L by 2 we have RL by 2 area 1 into E copper, and plus, and for the next part it's also compressive, so we would write RL by 2 area 2 E copper, that is equals to this one. And we have to represent the stress of steel also in terms of, we need to represent the stress of steel stress in steel also in terms of load. So we say P, or we can say reaction PL by AE, area steel, PL by A, area steel, ES. And here also we can say it's reaction R, then we have removed the length L. We say reaction R, area steel, ES, and we have to remove the sigma C. We say it's your R, uh, no, here is also that L by 2 has came into picture, so we need to do the calculation from the scratch itself. Up to this point, things are clear now. Delta net in the copper have to be equals to delta net in the steel. So for the free expansion of the steel, we have alpha steel LT plus, and on the steel bar we have tensile force of R L by A steel E steel. Then we simplify the equation. We say alpha C minus alpha S LT equals reaction R. We can do the reaction R and L in common. We can say reaction R L 1 by area steel is steel plus 1 by 2 A1 E copper plus 1 by 2 A2 E copper. So we can get the value of reaction. So your reaction becomes your length gets cancelled. We say alpha copper minus alpha steel into T, and you have to divide this part 1 by area steel E steel plus 1 by twice area 1 E copper plus 1 by twice A 2 E copper. Yeah, we know the values now. We can say alpha copper was your 1.5 10 to the power minus 5 minus alpha steel was your 1.2 10 to the power minus 5, and temperature rises by 30 degree divided by this one. 1 by area steel was your 100 square into modulus of elasticity was 10 to the power 5 Newton per square. So we can get the value in terms of Newton. This is per degree Celsius, and this is degree Celsius, and this one is your square. This is Newton per square. Finally, the answer would be in Newton. We can write plus twice 1 by 2 into area 1 was your 50 square into modulus of elasticity of the copper was 10 to the power 5, and for the steel it was 2 into 10 to the power 5, and for the third part we have 2 into area 2 was your 100 square, and the modulus of elasticity, Young's modulus, was 10 to the power 5 MPa. So your answer, if you solve the equation, you can get the value. You would get some value of R, and then we can say the stress in copper in the first part, that is equals to R by 50 square, and in the sigma C2 we have R by 100 square, and in this third part in the steel we have stress R by the area was 50 square. This is your Newton. So we would get the result in terms of MPa. We can say sigma steel is your 7.2 megapascal. That's 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 tensile force, tensile stress. That's your tensile stress. And in the sigma c1 is your 7.2 MPa. It is same because reaction is same, and your area cross section was same for the first part of copper, and but the force is nature is compressive. And in the steel, in the copper part 2, you have area more, so your stresses would be half compressive. Let's say go to the new topic, new question. You have a problem of, say, 3 bars are placed this one, this one, this one. Your alpha 1, you're having alpha 1, L is same, so we can write L is same. Your E1 is there, area 1 is there, area cross section, alpha 2, E2, A2, alpha 3, E3, A3. Now the question is saying calculate the actual change in length. Calculate the actual change in length. Get the change in length if temperature increases by T degrees Celsius. If temperature increases, what would happen? There would be, but this is a composite section. Okay, actually, this is a composite section. So if say material 1 freely expands by this amount, we don't know the values of alpha 1, we don't know these values alpha 2, alpha 3. So say alpha 1 expands this much, member 1 expands this part, equals to alpha 1 L T, and say material 2 expands, say this part, alpha 2 L T, and third part we don't know the values exactly. We can say, let's take lower value, say that is alpha 3 LT. But for the composite bar action, net have to be equals to, say, net have to be the net change in length is to be same. So we can say this is your final location. This is your final location. So on this part there has to be applied some force, reaction 3 we can say, and on this part some compressive, some tensile force, reaction 2. This one is also tensile, this one is also tensile, and on this part, first part, we can say this is your compressive R1. We can say summation fx goes to 0. We can write summation of all the forces are equal to 0. Writing this way as positive, we can say R3 plus R2 minus R1 equals to 0. But it's not it's actually, I am giving you how actually we can solve the question. But let's say alpha 1 was less, so R1 would have been tensile force. We don't know which one is compressive, which one is tensile. So it's not fair for R1 to be compressive here. So it can be tensile also. So for that we would say the final length, for the composite bar we can say for composite action, that's what the question is asking. Change in length. Change in length would be same for all the members. Change in length would be same in the all members in 1, 2, and 3. So we can write say the length initially was L, and the change is say say the change is say final length was uh, say final length was your delta. Final length was your delta, where it stabilizes. We can say uh, we can say change in length. We can say change in length of bars are calculated as, we say, it has expanded alpha 1 L T, and you have prevented some part. You have prevented some part. Yeah, wait. How can I say how to solve this? So uh, from the first approach, it's not fair for someone to be compressive or and someone to be tensile. So this method is not good way to solve the question. In the second method, we can have we can say the we can say that the forces that we shown here, R1, R2, and R3, they will be developed only for the part which they prevent. Okay, restraint is always preventing the part uh, which is like which is extra. For the material 1, we know final delta is your final location, but material 1 has expanded by alpha 1 LT, alpha 1 LT, but your final location of the overall composite is delta. If we subtract total minus final, we can say this is your difference. This part is your difference, and on this part your reaction 1 has been developed, or we can say stress 1 has developed. So for that part, your strain, this is prevented, delta prevented because of composite action. We know already, we know, say these trays are in a composite action. These are rigid plates 1, 2, 3. Say the force P was applied here. We can say uh, member 1 takes force P1, force 2 takes P2, member 2 takes P2, and member 3 takes P3. We say total force equals P1 plus P2 plus P3. Similarly, we can say uh, we can say for the material 1, the reaction developed R1 would prevent this amount of difference. So reaction 1, if we know the formula, like basic formula. This is your reaction 1. We don't know whether it's tensile or compressive. That depends on the values of alpha and delta. We say the reaction 1 is here. We can say delta equals R1 L by AE. So this delta is your delta prevented. When you prevent some deformation to happen, there is like stresses are certain to be developed. So your reaction 1 uh, because of that reaction 1, how much delta is being prevented? We can say delta prevented. We can write it in terms of this way also. So for the material 2, we have alpha 2 LT, and the difference minus delta. For that, we have reaction 2. Say the material has freely expanded up to this point, and it has to reach to the final location. So for this part it has to be, say, expanded. So this part, the difference of these two, we would be uh, writing here alpha to lt minus delta in order to get reaction 2. Say if the we don't know value of delta and alpha. If say delta is more than this part, so that means your delta was more. Okay, if delta was more and your alpha is less, your alpha is this less, that means it has freely expanded less. So on this material there would be tensile stresses developed. So this one have to be then this sigma tensile. Now for the material 3 we have alpha 3 lt minus delta. For the material 3 we can have force equilibrium. We would say summation of all forces equals 0. There is no external force. We say R1 plus R2 plus R3 goes to 0. And for the composite action, we say total deformations are same, and we can represent the deformations in terms of these reactions. So we know that delta equals PL upon AE. So this is your delta prevented. We can write P equals AE delta prevented by L. So we can say reaction 1 we can write as area 1 E1 delta prevented 1 is your alpha 1 LT minus delta upon length L is same for 3 members. And similarly for the material 2 we can write A2 by L alpha 2 LT minus delta. And for the material 3 we have alpha A3 E3 by L alpha 3 LT minus delta. The value of this total equals to 0. Now if we simplify the equation, writing alphas in one side and delta in one side, we can say let's take alpha A1 E1 alpha 1 and T we have plus A2 E2 alpha 2 T plus A3 E3 alpha 3 T, and we have to equate it with, see here is we write A1 E1 delta upon L plus A2 E2 by L delta plus A3 E3 by L into delta. So we can keep the delta common. We can write A1 E1 by L plus A2 E2 by L plus A3 E3 by L. That is equals to A1 E1 alpha 1 T, this one, summation of A1 AI EI alpha I into T. So your question was get the change in length of the composite bar. So your change in length of the composite bar we can have as summation AI EI alpha I into T by AI EI, and L is also there now. L we can write it, and it reaches to the top, we can write as this way: summation of AI. So it is a weightage factor of your actual rigidity. AI, nah, AE, yeah, AE is your actual rigidity. Now we know delta equals alpha LT. So your extra part here is this one and this one, and summation of AI. Let's take one of the best problems you would see in the chapter 1. You have a copper bar of 0.8 meter. This one is your copper bar of 800 mm, and another bar of steel of 600 mm. This is your steel. At C you have a 1 meter, 1 meter. This length is your 1 meter, and this length is your 1 meter. ABC is a rigid bar. Connected to steel bar and copper bar as shown. Now the temperature of the whole assembly rises by delta T equals 40 degree Celsius. We need to get the values of stresses in copper and stresses in steel. For the details of alpha copper equals 18 10 to the power minus 6 per degree Celsius. Alpha steel is equals to 1812, and your EC equals the area cross section for the copper is 400 600 mm square. For the steel bar you have 400 mm square. Here the bar ABC is rigid. That's what makes the question beautiful. Yesterday we also solved one question that was saying the bar is rigid. That means either the displacement of the bar is this way, this way, this way. It can't go this way or this way. It can't bend, or it can't deflect this way. Only possibilities are 1, 2, and 3. These are not true. For the rigid bar, these 3 conditions have to be satisfied. So how to solve the question when it's like lengthy? When it's a bigger question, you need to do free body diagrams. Let's say there is no external force, so we can say there's no external force. So let's say the force, let's say the force in the, actually we want to do the, we want to check the free expansion first. We want to see how much free expansion is possible. So from the free expansion concept, say free expansion, free expansion. For the copper, you have delta free copper, delta free expansion for the copper equals alpha copper length of copper into temperature T. So alpha copper is your 18 into 10 to the power minus 6 into length is your 800 mm, and temperature rises by 40 degrees Celsius. So if you calculate the value, the value comes out to be 0.5760 mm. And if you calculate the free expansion for the steel, you have alpha steel, L steel temperature increase. Alpha steel is your 12 into 10 to the power minus 6 per degree Celsius into length is your 600 mm, and temperature rise by 440. So your free expansion for the steel bar is 0.2880 mm. So from the free expansion study, we can plot how it looks like. Say this was your bar ABC of length 1 meter here and 1 meter here, and after that there was your, this was your A, B, C. Now you are saying that free expansion, you are saying the free expansion in the copper wire is this much, and in the steel wire this much. But if you see the problem itself, you have, see here the copper is fixed here, it can't go downwards, and steel also can't go downwards. There is only one possibility. If the copper expands freely, it has to rise by alpha copper LT upwards, and for the steel bar it has also to reach upwards by alpha steel LT upwards. So if the support is hinged here, pinned support, so it can rotate freely, and bar is rigid. We know if bar is rigid, these three conditions, any of these is possible. So if the bar is rigid, let's make the values now. So let's say the expansion is this much, and in this one it is this much. We know the values, actually it's like this. The expansion in the copper wire is, say this was your bar ABC. ABC is your bar 1 meter. Now they have to be rotated by some theta. The bar has to be rotated by some theta because bar is rigid. So now the sigma, we know the free expansion of copper, that is 0.5760. let's say 0.5760. say this one is your 0.5760 mm, and deformation in the steel, free expansion in the steel is your 0.2880 mm. But from the question, if we look from the physically from the problem, we say if copper is expanding, it has to go upwards, and steel has to also go upwards. But for the rigid bar, either three of these is possible. If it goes upwards, if it goes upwards, that means case 3 is not valid, because it is rotating downwards. It's not possible. And now checking for upwards or straight. Let's see. Now if the bar is rotating somewhat here, say slope has to be maintained, we can say, we can use the line. See, the slope has to remain continuous. For slope has to remain continuous, slope of rigid bar. So this has to be your final uh, displacement of the bar at different locations. So if this here it was 0.5760, it had to be get compressed by some delta copper compressed, and in the steel bar it has to get uh, expanded by some delta steel expanded. And for that, if you had to compress the copper, that means compressive force on copper is developed. Say the force in the copper is Fc, force developed in the copper. And let's say the force developed in the steel is tensile force, force developed in the steel. So if the forces are here, but we know that the external force is not, there's no external force. If there is no external force, we can say summation of all the external forces goes to 0. If in the bar if in the copper bar compressive force is developed, so we say if in the bar compressive force is developed, say this is your copper bar, compressive force of F copper is developed, and in the steel bar tensile force is developed, tensile force of FT Fs developed. So now by the normal reaction concept, this is your rigid bar, and here it is pinned. This is 1 meter, this is 1 meter. So at this junction the reaction is Fc, so it has to be upwards Fc, and here it has to be downwards Fs. So applying summation of moments at A equals to 0, clockwise is positive, we can say Fs into 2 equals to Fc into 1. So your force in the copper bar is twice the force in the steel bar. So we can write by the symmetric triangles, we can write from the similar triangles, from the similar triangles we can have delta final in the copper bar, that is 1 by 2 of delta final in the steel bar. See, if it is your final value, it is delta final copper, and this is your delta final steel. For 1 meter you are having delta copper, and for 2 meter you are having twice delta copper. That's your condition. So the delta final copper is initially it was 0.5760 mm, and you have prevented how much length change, that's equals to that's equals to the PL by AE, delta equals PL by AE. You know, for the copper, you got compressive force. You got compressive force. For the copper bar, you got compressive force, and for the steel bar, you got tensile force. And Fc equals twice Fs. So we can say for the copper bar, you got F copper, and PL. Length of the copper bar was 800 mm by area of the copper bar was 600 mm square. 600 mm square into modulus of elasticity was 10 to the power 5 megapascal, and the sign has to be here compressive minus na this one. This has to be equals to 1 by 2. Delta final for the steel is, initially it was 0.2880, and plus by the tensile force on the copper for the steel bar, we know the relation. F copper is twice Fs. Since F copper equals twice Fs, we can write all the values in terms of Fc. We can say Fs equals Fc by 2. This is PL. Length of the steel bar was 600 mm by area cross section for the steel was 400 mm square. Modulus of elasticity was, youngest modulus of elasticity is 2 into the 10 to the power 5 MPa. So when we solve this, we can get the value of Fc, that comes out to be equal to force in the copper bar, that's 28.40548 kilonewton. So the force in the steel bar is half of that, 14.20274 kilonewton. So from that, question was to get the value of stresses. So stress in copper bar is Fc by area cross section of the copper bar is 600 mm square. So we can get the value of stress, comes out to be 47.3 MPa, and for the copper steel bar, your stress comes out to be Fs by area cross section was 400 mm square. So your stress in the steel bar is 35.5 megapascal. This was a crazy question. Now we have the one last question for this temperature rise case. Say this one is your rigid block ABC. This is your rigid block ABC. A. This is your B, and this is your C. Here you are applying tensile force of 200 kilonewton, and the bar at B is made up of bronze. This is your bronze, and on the sides you have steel posters of 1 meter length. This is 1 meter steel and 1 meter steel. So the assembly is subjected to temperature rise of 20 degree Celsius. Question is saying get the values of stresses in the bronze and steel if the rigid bar ABC has to remain horizontal. If it has to remain horizontal, get the value of stresses. So how can we solve this question? See, before this question, your previous question was like this. There was no external force, and we just calculated the effect of free expansion. Then we calculated the reactions and got the stresses. Here we can have here we can use the superposition because you have load. We can solve load individually and the temperature rise individually. That way we can also do. Let's take first the loading diagrams also first. Say the reaction in the steel bar is Fs. Since these two are equally spaced from the center, and load is also applied at the center, these Fs1 and Fs2 are equal, and force in the bronze, F bronze, so we can say Fs plus F bronze plus Fs has to be equal to 200 kilonewton. So let if your free body diagram is this one, we can say if the force in the bar is Fs this way, and in the bronze it is like this, and in the steel we have. So if it is here, if it is downwards, it has to be upwards in the rigid bar ABC, Fs, Fb, and Fs, and your load is 200 kilonewton. So we can get the value of Fs and Fb? No. This part is your effect of external force 200 kilonewton. Now if we calculate the effect of free expansion now, say the expansion in the steel bar is delta steel equals alpha steel, length of steel, and temperature increase. Your alpha steel, that's 12 into 10 to the power minus 6 into length of steel bar is your 1 meter, and temperature increase of 20 degree Celsius. And delta bronze, that's alpha bronze, L bronze, T. Alpha bronze is your 20 into 10 to the power minus 6 into length of bronze is 1500 mm into temperature rise of this one. Now we got these values. We had to calculate the values. 12 into 10 to the power minus 6 into 1000 into 20. That comes out to be 0.24 mm and this one comes out to be 0.6 0.6 mm. Your condition that the question has imposed that bar ABC has to remain horizontal. We know that the amount of deformation in the steel bar and in the next steel bar is same. If say here it is fixed, here it is fixed, and here it is fixed. So if they expand, so there is only one possibility that they will go downwards. Say this goes downwards, this goes downwards, and this goes downwards. But the bar has to remain straight. That's possible. Say if the steel bar, if the A point has to go, let's take this as reference line. If the point A has to go downwards by delta A, that would be same because the ends are made up of steel bars. So delta at C is also same. And for the rigid bar, the deformation in the bronze is also has to be same. So this is the final position of the bar, delta B. So this is the final position of the bar, and this is fixed location, this and this. So your condition becomes like, we can write deformation in steel bar and final has to be equals to deformation in bronze bar final. So we had combined the two effects, one of the loading and second one of the free expansion. Let's take for the steel. We know the free expansion for the steel, that came out to be 0.24 mm. We can write 0.24 mm. It was downwards, and in the bar we can say delta S final, this one, that is equals to delta free expansion plus delta because of loads. So combining the two effects, for the free expansion we have delta S equals to 0.24 mm, and because of this loading we can have force Fs. This is your tensile force. You can have tensile force. So this is all positive, plus force in the steel bar, Fs, L of the steel bar, area of the steel bar, E of the steel bar. That has to be equal to delta bronze final. Delta free expansion of the bronze was 0.6 mm. 0.6 mm. And say the force in the bronze is Fb, that is also tensile, length of bronze, area of bronze, E of bronze. So substituting the values, we write 0.24 mm plus fs, length of the steel bar was 1 meter, and for that 1.5 meter. We write as 1 meter by area of the steel bar. Area of the steel bar is what's the area of the steel bar? Area of the steel bar is 900 mm square. This one is your 900 mm square, and for the bar bronze, we have area of the bronze as 1500 mm square, and modulus of elasticity of bronze of the steel is 205 in 10 to the power 3 Newton per mm square. And for the bronze, we have modulus of Young's modulus equals to 82 into 10 to the power 3 Newton per mm square. Your force in the bronze, Fb, into length of bar of bronze is 1500 mm plus 0.6 mm equals this. So we know the relation between Fs and F bronze when we calculated the summation of moments. Have we? Yeah, we know this relation from the summation of forces. We can say F bronze equals to 200 kilonewton minus twice Fs. Yeah, 200 minus Fs. So we can write F bronze as 200 minus F steel. So after solving, you would get the value of steel. Force in steel equals to 93.89 kilonewton, and force in the bronze comes out to be 112.214 kilonewton. So stress in the steel is equals to Fs upon area of the steel bar was your 900 mm square. That comes out to be 104.3 megapascal, and sigma bronze comes out to be equals to 8.14 megapascal. Hope you understood the problem. Now we have next topic. That's your Poisson ratio. Poisson's ratio. We write it mu or 1 by nu or 1 by m. Poisson ratio. Say we studied, you have a bar, you applied force P tensile, it changes to L plus delta L. So with increase in length in the longitudinal direction, if we check the cross section, say we are talking about two-dimensional value, say for the area, say for the area to remain constant, you know, for a rectangle, when area equals, initially it was LB, and final area it is L plus delta L. So your B is changing also in order to maintain the total area. So we'd say B dash. That B dash, since L plus delta is the L plus delta L is more than L, so B dash has to be less than capital B. So with we can say with, say, for tensile force, we can say for tensile force in the longitudinal direction, say for the tensile force in the longitudinal direction, longitudinal, we can say axial direction, this is your longitudinal axial direction, uh, with increase in length, we got delta L increase, this has increased, there is decrease in B, that's delta B, decrease in the lateral direction. So in one direction, if your length increases, in the other direction your length decreases. Say we studied the malleability, you are applying hammering on the metal, this was your metal, you applied force, compressive force, so it became into sheets, so you are applying compression in this direction, so it's getting compressed, but in the lateral direction it is spreading, so your final metal becomes in terms of plate, so your depth becomes less and width increases. So if your material gets shortened in the direction of load, in, we can say, axial direction, and so it would elongate in lateral direction to load, elongate in lateral direction to the load. That's what your Poisson ratio says. So your Poisson ratio says let's say you apply stresses, let's say you apply stress in longitudinal direction as sigma x, say it's your y axis, this is your x axis, and this is your z axis. We say that x is your axial direction for this load, axial direction or longitudinal direction, and y and z are your lateral direction. So your Poisson ratio says that mu equals minus lateral strain by axial strain. Minus lateral strain by axial strain. Your negative represents that in if your axial strain is say tensile, your material has been elongated in the axial direction. In the lateral direction, it has to be getting shortened. So that's what your negative symbolizes. So we know strain. We know strain equals, we can say, for your reference, we have kept the x-axis as your longitudinal axial axis. We can say for the lateral strain, we have lateral strain is your strain in y by strain in x. That's, we can also have in 3D, we can say minus strain in z by strain in x. Yeah. So your strain in y comes out to be equals to minus times mu strain in x. Similarly, strain in z comes out to be equals to minus mu strain x. We know strain is your change in length. Strain x is your change in length. If this if the length of the bar is L, your width in the Z is B, and depth is D. We can say strain in x is your delta L upon L, and strain y, that is minus mu times strain in x. Your strain in x is delta L upon L. but the strain in y is actually equals to change in depth with respect to total depth, and strain in z, that's equals to delta b upon b, change in width upon total width. So now we have value of mu is ranging from 0 to 0.5. 0 is for cork, that's used in bottles. There's soda bottles. That cap, this cap, it has a value of 0. Your 0 means mu equals 0 means your if lateral and axial. That means upon applying the axial force on the bottle, like after you fix the cap or release the cap, you apply the force in the axial direction, there would be strain in the axial direction, but there is no strain in the lateral direction. If there is no strain in the lateral direction, there is no stress in the lateral direction. That helps to prevent the leakage of the juice and to prevent any bursting of the walls of the bottle. So we want strain in the lateral direction to be 0, and for that we use a material cork for the bottles. So your mu equals 0, and mu is 0.5 for plastic. Your rubber, that is called as perfectly elastic rubber, and this one is of most often asked. The mu of steel is approximately equal to 0.3, and mu of aluminum equals to 0.33, and mu of cast iron you can take around 0.2 to 0.3, say 0.26. So these are some values. Now let's do the analysis by the concept of this Poisson ratio. Let's take the case 1, that's uniaxial loading. That's in only one direction, only one axial, only one axis. Loading is passing. Uniaxial loading. You have length L. You are applying force P in the direction. Say because of that you would get sigma x. Now we would represent loads in terms of stresses. So it is your sigma x only acting. There's no, that is sigma z and sigma y equals to 0. So we want to calculate like strain in y, strain in z, strain in x. So we can say that strain in x, that is equals to change in length upon original length. That equals to, we know delta equals PL by AE. We know delta by L is your strain in x, that's P by A. P by A is your stress in x, and sigma x by E. We can say your strain in x becomes sigma x upon E. Now if we want to calculate the strain in y, say it's your y axis. So strain in y is yours from the Poisson ratio. We say mu equals minus lateral strain by axial strain. So we have strain in y equals to minus mu times strain in x. So we can have minus mu times strain x by E. Okay. Similarly we can have strain in z minus mu times sigma x by E. So in the both, we can conclude that in both the directions strain is same. It's only a function of sigma x. Here it is a function of sigma x only. So strain, uh, longitudinal axial strain is accompanied by lateral strains. So the lateral strains are both equal. So now the next one is your biaxial loading. Biaxial loading. Let's take sigma x and sigma y is acting. Sigma z is 0. Sigma x and sigma y is acting. Let's say this is your sigma x and this is your sigma y. Let's take the dimensions as we say, length is L, area cross section, you have B, your depth. This is your sigma x. So we want to calculate, so we can do the superposition here. Superposition theorem. Solving individually. Your separate individual case was sigma x, and similarly we can have this case also, sigma y. Now solving for individual cases. So we know strain in x equals, we have calculated, it comes out to be sigma x by E. Strain in y, we have strain in y comes out to be minus mu times strain in x. That strain in x was sigma x by E. Similarly, strain in z, but we don't worry about that. Say sigma x by E. In this case, your sigma x by E, we don't know as of now. But the thing is, what we know that the load passes in y direction. So your axial direction, your axial direction is y. So your axial direction is becoming now y. Y is your axial direction. So your strain in, we can say strain in y equals minus time. We can say strain in y equals stress in y by Young's modulus of elasticity. This is this way. The direction of stress, we keep that as axial. Okay, that direction we keep as axial direction. So now to calculate the value of Ex, we can say Ex equals, we know mu equals lateral strain by axial strain minus times. So your axial strain in this case is Ey, and your lateral strain here is Ex. So your Ex becomes minus times mu Ey. So your strain in y comes out to be minus mu times sigma y upon E. So if we combine the two effects, we would say final strain in, final strain in x equals to sigma x upon E minus mu sigma y upon E, and strain in y comes out to be equals to sigma y upon E minus mu sigma x upon E. Similarly, you can have, no, just take it as now your third case, that is triaxial loading. Triaxial loading. Say you have a cube Now you are applying stresses in all directions. Say it's your sigma x, it's your sigma y, and this one is your sigma z. So we can say, we can now combine the effects. Similarly, we can do this superposition here. We can say it is your sigma x, and it is your sigma y, and it is your sigma z. Then we add them, then we get the result as we got earlier this way. Then we can conclude, we can say final strain in x equals sigma x upon e minus mu sigma y upon e minus mu sigma z upon e, and your strain in y is sigma y upon e minus mu sigma x upon e minus mu sigma z upon e, and sigma strain in z, that's equals to sigma z upon e minus mu sigma x upon e minus mu strain upon sigma y upon e. Now these are the general results. From this case you can get the first two cases also. So for the uniaxial loading, there was only sigma x acting. So if we remove the sigma y here, it comes to 0, sigma z comes to 0, so you will only get this part. That's what we had derived earlier. Now we would calculate volumetric strain. We know strains are of two types. One is your normal strain. Next one is your shear strain. Normal strain, we have here strain x, strain y, strain z. This is because of these normal stresses, sigma x, sigma y, sigma z. These three are because of sigma x, sigma y, sigma z. So we call them as normal strains because of normal stresses. So if we add these three, we would say it is volumetric strain. Volumetric strain, that's also called as dilatation. So that's what we are solving now. Volumetric strain. Take an element, say length is L, width is B, depth is D. So your volume, initial volume is length, breadth, depth. Say after the application of stresses, after the application of stresses, the final volume comes out to be equals to I would say, let's say the length L has been changed to L plus delta L, and B has been changed to B plus delta B, and D has been changed to D plus delta D. The delta L, delta B, delta D, it can be positive or negative, anything. If one is positive, others may be negative, in order so that the volume in the normal strain is conserved. Okay. Now, so if we do some trick here, we can say, let's take out L common from here. We can say L1 plus delta L upon L, B1 plus delta B upon B, and D1 plus delta D upon D. We have LBD 1 plus delta L upon L. That's your strain in x direction, keeping the x as the actual direction. and 1 plus EY and 1 plus EZ. This is your X, Y, Z. So your equation comes out to be equals to, so your V final equals V initial 1 plus EX 1 plus EY 1 plus EZ. So your volumetric strain, is change in volume upon original volume. Your change in volume is V final minus V initial. Your V final is V 1 plus epsilon x 1 plus epsilon y 1 plus epsilon z minus initial volume was your V by original volume was your B. So if we take a V common, we can get 1 plus EX 1 plus EY 1 plus EZ minus 1 upon V. So your value comes out to be equals to, let's say, 1 plus EX So if you solve this one, we can have 1 plus EY plus EX plus EX EY 1 plus EZ minus 1. You can say it's 1 plus EY plus EX plus EX. Since the strains are very small, we are dealing with strength of material that's within the elastic limit, that 0.1 mm part in a 100 mm length of specimen. So the strains are very small. So we can say if strains are very small, like 10 to the power minus 5 of the order of this value, if we multiply these two, this is very negligible. So we can ignore this part. Almost we can say it's equals to 0, and then we can have this 1 plus EZ minus 1. Then after solving, we can say 1 plus EZ plus EY plus EY EZ EY EZ plus EX plus EX EZ, and finally minus 1. So similarly, we can say we can ignore this and we can ignore this, and we can have final volumetric strain equals to EX plus EY plus EZ. Now also we know the results in the triaxial loading, the value of EX, EY and EZ. We can say that's equals to strain in X by E minus mu, strain in Y upon E minus mu, strain in Z upon E, plus value of EY is sigma Y upon E minus mu, sigma X upon E minus mu, sigma Z upon E, plus for the strain Z we have sigma Z upon E minus mu sigma x upon E minus mu sigma y upon E. So after the simplification of this result, we can get sigma x plus sigma y plus sigma z upon E 1 minus 2 mu. This one. So now if we want that volumetric strain should be 0, for volumetric strain to be 0, what are the conditions? So for the volumetric strain to be 0, we can say 1 minus 2 mu can be 0, or sigma x plus sigma y plus sigma z equals 0. If 1 minus 2 mu equals 0, that means the value of mu should be equals to 0.5. And this value of mu equals 0.5 is if we have incompressible fluid, there we can have no volume change. That's no volumetric strain, no volume change. Incompressible fluid is that's no change in volume with change in pressure, no change in volume with change in pressure in the fluids. For that we can have for the incompressible, we can say that for the incompressible fluid your mu should be equals to 0.5, or sigma x plus sigma y plus sigma z has to be equals to 0. This is only possible when say one is tensile, other is compressive, and next one is compressive or tensile, so that the resultant of sigma x plus sigma y plus sigma z equals to 0. One should be of the opposite sign. Anyone, it can be anyone. Yeah, let's take one problem. You have a cuboid. This is your cuboid. Say this length is 400, this is 200, and this is your 500. mm. Now the stresses that are applied, your sigma x is compressive, equals to 300 megapascal. Your sigma y is tensile, sigma y 200 megapascal, sigma y, and sigma z, it's your tensile 400, sigma z is your 400 megapascal, sigma z. We need to calculate, get the value of strain y, and get the value of change in volume. Strain in y, we know the result. For the strain in y, we have sigma y upon e minus mu, sigma x upon e minus mu, sigma z upon e. So if we solve this, we know sigma y is your tensile stress of 200, and your modulus of elasticity, we know for the steel we have E equals 210 gigapascal, and mu equals 0.3 for the steel. So your E equals to 210 into 10 to the power 3 megapascal. This is your megapascal. This is your megapascal. So minus mu, your mu is 0.3 into sigma x minus mu sigma z. Sigma z is your 400 upon E is your 210 into 10 to the power 3 megapascal. For the stress x, we have compressive stress. We have compressive stress of 300, so we have to represent it as minus 300. So after solving, you can get the strain value. Strain y equals to 10 to the power minus 4. And if you want to calculate the change in length in y by original length in y, we can get the value of change in length in y. Y is delta Ly equals to strain in y into length in y. Your length in y is 500. Your length in y is your 500, so the value comes out to be equals to 0.404 mm. Now if you want to calculate the volumetric change, for the volumetric change you need to calculate change in volume. For the change in volume, we know volumetric strain equals change in volume by original volume, and we know the result we derived that sigma E, that volumetric strain equals sigma x plus sigma y plus sigma z upon E 1 minus 2 mu. Then if we substitute the values here, sigma x is your minus 300 because compressive, plus sigma y is your 200, sigma z is your 400, by Young's modulus of elasticity is your 210 into 10 to the power 3 megapascal. This is also megapascal, into 1 minus 2 into mu is your 0.3 for the steel. So your strain, you get the volumetric strain. That's equals to delta V upon total volume. Initial volume is your LBD, your 400 into 200 into 500 mm cube. So we can get the value of delta volume, change in volume, that comes out to be equals to 22857.14 mm cube. Let's say all of these three stresses were compressive. Let's say all the three stresses were compressive. Sigma y, sigma z, sigma x, and your sigma z. So your then we can get volumetric strain as minus, sigma y is your minus sigma y upon E minus mu sigma x upon E minus mu sigma z upon E. Now coming back to our next problem. Say you have three metal cubes. You have three metal cubes. So you have three metal cubes. The three metal cubes are placed in contact with each other. This is your A, B, C. Each of the cube is 100 of side 100 mm. They are in direct contact, resting on a rigid base. This is your rigid base. Rigid base. And confined in x direction. This is your x direction. They are confined in x direction. That means in the x direction they are not able to move. They can't move in the x direction. Restrained in, we can say, restrained in x. If the upper face of the center cube, you know, this cube B is subjected to stresses of, this is your stress, or we can say this is your stress. Stress on B equals to sigma y 0.5 kilonewton per mm square. We can say that is equals to 500 megapascal. So this is your question. Now question is saying that the compute for the cube B. Now for the cube B, get sigma x, get the value of sigma x, strain x, strain y, strain z, volumetric strain. Yeah. So we can say summation fx goes to 0. If we say summation fx goes to 0, there's no external horizontal force. So we can say let the reaction at A equals RA and reaction at C equals RC. Assuming them say RA is acting this way and RC is acting this way, we can say RA equals RC. Say that's equals to reaction R. Now if we have the free body diagrams of the three cubes, we can say this is your R. So here it has to be R. So say it's compressive. Since you are applying stresses on the material B, it would try to expand in the lateral direction, as that of hammering. You are applying compressive force in the y direction, so it is trying to expand in the z direction and in the x direction. In the x direction, you are preventing the deformation, so stresses or reactions would be developed. But in the z direction, you are not preventing any strains to restrain, so strains in the z would be developed. So in the x direction, we say this is your minus, and for the next cube B, you have stress of sigma y equals to 500 MPa, and here we have a reaction of r equals to, we don't know the value of r as of now, and for the third one it's also the same, this way, r. We know the one condition that we can write we know that strain, or we can say the compatibility condition says total change in length in x direction equals 0. So because of these loadings, total change in x direction is equals to 0. So if you write the change in length in x direction equals to 0, we know delta 1 equals PL upon AE. We can write as R L. We know the value of L since all the cubes are of size 100 mm. This is your 100 mm. So we can write total change in length, that is your R minus R L. L is your 100. Area is your 100 square. The cross sectional area is your square. We can say it's 100 square. E for the materials we have different value of E. For the material A and material C we have value of E equals to, here value of E equals to 150 into 10 to the power 3 megapascal, and value of mu equals to 0.25. Same is valid for the cube C. For the cube B we have E equals to 200 10 to the power 3 megapascal, and mu equals to 0.3. So we can say E is your 150 into 10 to the power 3, and the answer would be in newtons. So we can say this one, the reaction R would be in newtons, I am saying. So this was your effect of the cube A. For the cube B we have two stresses. For the stress in x direction we can write easily minus R 100 upon area cross section 100 square. E is your 200 into 10 to the power 3 plus, now the using that Poisson ratio, if stress in y is your 500, we can say strain, we have strain in, we can say strain, we can write strain in x equals to mu times strain in y. For this loading, strain y is your axial strain. So your axial strain becomes minus mu sigma y upon E B. This is your Ex. So Ex for the B equals this. We know strain equals to change in length of B, change in x of B by original xb equals to minus mu sigma y upon E B. Your value of x in B equals to value of side of cube 100 mm. So we can write minus mu is your mu B, that is 0.3 into sigma y. Sigma y is your 500, but it's compressive, minus 500 MPa upon E of B is your 200 into 10 to the power 3 megapascal. This is your strain in x direction because of the stress in the y direction, that is 500. But we don't want strain, we want change in length. Change in length is like you multiply it with the cube length 100 mm. See, you are applying compressive force on the B. You are applying compressive force on the B, so your negative and negative becomes positive in the x direction. That means it's becoming sheet in the x direction. So your length increases in the x direction because of compressive force in the y direction. Okay, this was your part B, and third one is your reaction R. Length is your 100, and area is your 100 square. E is your 150 10 to the power 3. This all equals to 0. This is your compatibility condition. So we can get the value of R, your value of reaction, that comes out to be something. R comes out to be something. You can calculate. Once you got the R, you can say sigma stress in the cube A equals to reaction you got by area square, that is A square, that is your 100 square mm square. That you can get stress value of 41 megapascal compressive. So similarly, that stress is also equals to sigma C. In the cube C, the stress is also same. Now we have to calculate the stress in x direction that we get calculated. That's what the question was saying. The strain in x is the strain in A, strain in B, and strain in Z in x direction. Strain in C in x direction. Now we want to calculate the strains in EX, EY, and EZ and EY. So your strain for the cube B, now we have the loading for the B as this way. You have a stress of 41 MPa and a stress of 500 MPa on the cube B. So we need to calculate strain X, strain Y, and strain Z. So strain X is your sigma X upon E, sigma X upon E, EB minus mu. Mu is your 0.3. Sigma Y is your minus 500 upon EB. So you can solve it. You can and get the value as 5.45 10 to the power minus 4. Strain in Y is your sigma Y upon EB minus mu, sigma X minus mu, sigma X upon E B, that comes out to be equals to minus 2.44 into 10 to the power minus 3. And strain in Z equals to, when a stress in Z equals to 0 minus 0 by E minus mu minus mu, strain in X, stress in X by E minus mu, strain in Z by E, that comes out to be equals to so your volumetric strain is summation of EI, that equals to minus 1.0835 10 to the power minus 4. See, the strain in Y is your negative. This is negative because your stress in X, stress in Y is very much, 500. Strain in X is your very less, 41. So your strain in Y is compressive, negative. So net volumetric strain is negative. Let's take one problem. You have a stepped circular bar hanging under the self weight. You have bar 1 and you have bar 2. Length here is L1 and length here is L2. Diameter here is D1, no, D2, and diameter here is D1, and the cross section is circular cross section. So we need to calculate the total deflection under the self weight. Total deflection is deflection of bar 1 and bar 2. We know the result of prismatic bar subjected to having the hanging under the self weight. We have the deflection equals to gamma L square by 2e. We know that if you have the gamma as unit weight for the length one, L1, we can say it is like this. So we can say for the delta 1, we have gamma L1 square by 2e, plus for the bar 2 under its self weight, we can have the delta 2, that equals to gamma L2 square by 2e. But there is something more plus delta more. See the variation. If you want to check the variation of the weight along the length, we can say here the weight would be 0, and the weight is varying at each x. At each x, weight is varying and increasing upwards, and reaches to W at L1. Then the weight is okay. And for the bar 2, we can say for the bar of L2 length, we can have its variation as this way. We can say the here the weight is 0 for the bar L2, and maximum weight is at the top, but it is hanging. So this one is your weight 2. This one is your weight 2. This one is your weight 2, and this one is your weight 1. Weight 1 is your gamma into volume 1, that's gamma pi by 4 d1 square L1, and weight 2 is your gamma volume V2, that's gamma pi by 4 d2 square L2. But here, because of this part, its its effect is acting as and concentrated load on the bar of length L2. So its effect is similar to that of a bar of weight, we can say weightless bar subjected to load P. So at each fiber, at each dx, we have weight variation as this one. So your weight variation. So this part is your weight variation of this one is your W1. It's constant. So that delta more we can calculate as we know the formula, that is PL upon AE. So your delta more, that comes out to be equals to, for the P, what's the value of P? Can you calculate the value of P? P is the weight of bar 1, that's equals to, we know, gamma pi by 4 d1 square L1. So we can write here delta more as gamma pi by 4 d1 square L1. Okay, and your P L is for the length 2 PL by AE, area of the area cross section for the bar 2, where we are focusing on the bar 2 now. You are applying force P on the bar 2. Okay, your bar 2 area is pi by 4 d2 square, and E of the bar, E is constant for the two bars, so we can get this value. We can say gamma by 2 is common. You can say L1 square plus L2 square plus this part, and you simplify it, you would get the result. You can get the result as gamma. You can get the result as gamma by 2e L1 square plus L2 square plus L1 L2 by d1 square by d2 square. Then let's say let's have a problem. Say your diameter 1, say your d1 equals to 100 mm and diameter 2 equals to 70 mm. Then we can, and length 1 and length 2 equals to say 1 meter. We can calculate, and gamma you can say gamma equals to 8 into 10 to the power 5 minus 5 Newton per mm cube. Poisson ratio 0.2. Calculate the value, and you can get the value of deflection. That comes out to be elongation comes out to be equals to 5.96 10 to the power minus 4 mm. Now next part of the question is saying you have this bar and you have this bar. This is 1 meter and this is 1 meter. It's saying at 500 mm from A, that's at 500 from A, there is a section, AA section. Get the diameter, get the change in diameter, of bar of diameter here is 100 mm. So we want to calculate the change in diameter. Since your strain in, we know the strain in, we calculated the change in length in this direction, delta L total. So the effective would be, we know that we have given Poisson ratio also. So based on the Poisson ratio, we can calculate lateral strain, that is along the diameter that's perpendicular to the this length. We can have diameter. So there would be change in diameter upon increase in length. There would be change in diameter that we need to calculate. Yeah. So if you want to calculate the change in diameter, we say the lateral strain, that is strain in the diameter, or lateral strain. Let's say strain in Y, strain in X. Say it's X direction. So strain in X is equals to mu strain in Y. That's equals to minus mu. What's strain in Y? If we know strain equals to stress by Young's modulus, we can write stress by E. What is the, at this section we need to calculate? Here there would be some stress. The value of stress at that location we can calculate. We need to add a total weight below this section. All of the weight has to be calculated. So that then we divide that load by this area cross section, we can get the stress acting at this point in the y direction, sigma y. So the sigma y at that section, that comes out to be equals to stress is equals to P by area. So we can write as your total load is gamma pi by 4 uh, gamma into volume. For this part we have volume equals to pi by 4 diameter 1 square length 1 L1 plus for the next part, this part your length is only 500 mm. You can write gamma pi by 4. Your diameter here is 100 mm square and length is only 500 mm. You can get the value of stress y, this load y divided by, then you divide by it by pi by 4 diameter 1. Diameter here is 100, so we can write 100 square. Then we can get the value of stress. That comes out to be equals to 0.0792 megapascal. So we can say change in diameter equals to minus 0.0792 into divided by E was your 2 into 10 to the power 5. So this was your change in this was your strain in x direction, that is strain in along the diameter. So if you want to calculate the change in diameter, you can say strain in along the diameter axis, lateral axis into diameter. That equals to, that comes out to be 7.92 10 to the power minus 6 mm. That's negative. Negative means it has decreased. Because it was negative, it's negative. So diameter has been decreased because length increased, so along the diameter it would decrease. So next one, is your, say you have a this spring, you apply force P, the spring has stiffness K, then it gets displaced till it balances the load K equals P equals K delta. Say it's elongated to some delta, so P equals K delta. Then similarly we can have for the bar, you applied force P, then your deflection was PL upon AE. If you write it in terms of P, we can say P equals AE by L into delta. So your AE by L equals to stiffness of the bar or stiffness of the beam into delta. So we can idealize a beam or a bar in terms of spring with stiffness K equals to AE by L. So stiffness is your stiffness K is P by delta. That's for unit displacement. For unit displacement or deformation, how much load is required to deform a particular spring or a bar to 1 mm, how much load it requires to get deformed to that 1 mm. That's your stiffness. If your stiffness is more, that means you need a lot of load to get deformed or displaced. Okay. Now if we have a question of, say we design a question, you have a steel bar of length L, and you connected it with a spring of stiffness K. Then you raise the temperature to 2 degrees Celsius. We need to calculate the stresses. We need to calculate the thermal stresses, get the thermal stresses. So we can say the external forces are not there. We can say summation fx goes to 0. Let's say the reaction here is R. We can say the reaction here is R. It is also here R, and in the spring it is also R, and here it's also R. So we can say compatibility condition yours says, we can use the compatibility condition that delta total in x equals to 0. So if you calculate the total deformation in x, it has to be 0. If we calculate for the first one, this is compressive, we can say R L by area steel E steel plus your spring is getting compressed. Spring is getting compressed by, say, some delta dash. We can say that delta dash equals to your force in the bar minus force in the bar, because it is getting compressed, divided by stiffness of the bar, stiffness of the spring. Delta equals E by K, and this is because of the loading effect. If we have the effect of thermal stress, because temperature is because of the temperature variation increase, your length of the bar is also increasing. So your length of the bar is increased by, say, alpha L T. It is increasing. We can rate it as positive, and these two are preventing the deformation, so that net deformation in the x goes to 0. Yeah. So if we calculate it, we can say you have we can write as 1 plus AS ES by L, 1 plus AS ES by L into KS into RL upon AE equals to AL alpha LT. Then you calculate, we know R by A is your thermal stress, then you can calculate the value of thermal stress. That comes out to be equals to, we know already value of thermal stress is EAT when there was only a bar fixed between two fixed supports. It was EAT. When there is also a spring, then we can get the value into 1 by 1 plus K bar upon K spring, where the K bar is your A E by L. Let's take one more. You have a question here. A bar between two fixed supports, but the temperature variation along the length is in terms of say at any x, your temperature at any x has been raised by T naught x cube upon L cube. At x equals to 0, your temperature is T naught, and at x your temperature is 0 raised, and at x equals to L, your temperature becomes T naught. Your temperature raised becomes T naught. So we need to calculate the thermal stresses, sigma thermal. So we know because of the thermal variation, we can say we have delta, we know alpha LT, but your time your T is not constant. It is varying with the length. So we can say it's of the Tx, and since the temperature is varying along the length, so we need to take a particular strip anywhere. Say if you take a strip at x of dx, so we can write it as alpha dx delta strip. So delta strip is your alpha dx dx. So we can write delta total, this is your free expansion, that is equals to 0 to L alpha dx, and your tx is your value of tx is T naught x cube by L cube, and your dx. You calculate it, you get delta free equals to alpha t alpha lt by 4. Now you need to calculate the thermal stresses. So this delta free has to be prevented by the supports. Let's say the supports are applying a force of R in this direction. Summation fx goes to 0. There is no external force, so your R has to be equal and opposite. So they will compress the fibers. So compatibility says, compatibility condition, that minus R L by AE equals to minus plus alpha LT by 4 equals to 0. So your thermal stress, sigma thermal in the bar, that comes out to be equals to EAT upon 4. Yeah. Now we studied like the normal strain. Now we studied normal strain. Now we are coming back to next type of strain, that is shear strain. Shear strain. So if you take a pure shear case, that is only shear stress is acting, no normal stress is acting. Say take out and you take an element, then you apply shear stresses. This is your tau xy, this is your tau yx. From force equilibrium, tau xy equals to this tau xy in opposite direction, and tau yx equals to tau yx in this direction. And for the moment, from the moment equilibrium, we said that the complementary shear stresses, these are equal to like tau yx equals to tau xy at because of moment equilibrium. So we can do the superposition here. If we separately examine the forces, the stresses, let's take these stresses, tau yx. Yeah, it doesn't matter, we can write tau xy. Because of this, you can think of a box. We can think of jute ka dabba. Like if you apply forces, one force at the top you apply in this direction, and the bottom you apply in this direction. So material would there would be a change in the angle between the axes. So your shear strain, we can write shear strain is axes के बीच का एंगल चेंज होना. So if your initially the angle between the two axes was 90, so after that there will be distortion, that we call as distortion. In the shear strain, one more point, in the shear strain there is no volume change. In the shearing, because of the shear strain, there is no volume change. But in the normal strain, because of normal strain, we have volumetric strain. We got normal volumetric strain that we called as dilatation. So because of normal stresses, you can have change in volume, but because of shear stresses or shear strains, you don't have volume change. There's only distortion, that is volume change without, that's change in axis angle, change in angle between the axes, change in angle between the two axes. That's called as shear strain. So if we check it, we say that, let's say this fiber goes to somewhere here, and this fiber goes to somewhere here. Then if we combine them, we can get somewhere this way. Let's say it has been shifted to some theta 1 plus. Next one is your tau xy acting in this direction. So this would try to move the that box here in the upward direction, in this side downward direction. So we can have somewhat like this. So then we join them, so we can have here angle change theta 2. Then your shearing strain, then your shear strain will write as gamma xy. That is the change in that is the shear strain corresponding to plane xy. Shear strain corresponding to plane xy. That is equals to theta 1 plus theta 2. The combined effect of these two loadings, we call that as shear strain, that is theta 1 and theta 2. But we know from the complementary shear stresses that tau xy, tau yx equals to tau xy. So your theta 1 equals to theta 2, which implies gamma xy is your 2 theta. So if you represent shear strain in terms of strain matrix, if you have a strain matrix, we can write gamma ij, we can write as gamma xx, gamma yy, gamma zz. So it is gamma xy, gamma xz, gamma yz, gamma zy, gamma zx, gamma yx. So but the thing is, we know the stress matrix was your tau ij was your sigma x, sigma y, sigma z, tau xy, tau yx, similarly tau xz, tau zx, tau zy, tau yz, tau zy, tau yz. So then we have that normal because of the complementary shear stresses, tau xy was equals to tau yx. But since because of tau yx, how much change in angle is there? Because of tau xy, there's only change of theta. That theta equals to gamma xy by 2. So we have to represent, because of tau xy, there is only a change of theta 2. That so that we have to write as gamma xy by 2. The total gamma xy by 2 is because of the two effects, because of tau xy and because of tau yx. It contributes to, say, theta 2, it contributes to theta 1. So similarly, we have to write here divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. So this is your strain matrix. And gamma x, this one is yours, while we know that this one is your strain z, this is your strain y, and this is your strain x. So this is what we have completed. We have that we know that stress proportional to strain from the stress strain curve. Then we got the initial portion as we said that slope is equals to stress by strain. Similarly, it was in the universal testing machine, in the tension test. But if we apply torsion test, in the torsion test, we get G proportional to gamma. Tau equals, we have shear stress proportional to shear strain. Then we write gamma tau equals to G into gamma. So we have now the relation between elastic constants. We have the relation between elastic constants. Relation between elastic constants. say your elastic constants are E, G, K. Okay. If your value of E, G, K are more, that means your material is very stiff and strong. So your deformations are small. If they are more, that means deformations are small. Uh, we have the concept of homogeneous material. Homogeneous material is if there is a body at a point, a property, if they're in a particular direction, if the property is E2, and if you take any point, other point in that same direction, the property is same. So in one direction, property, it can be any property is same, but at the same point in the other direction, say this one, property is E1. Now if you have next one is your isotropic means in all directions your property is same, but at a point if you have a particular point at each direction, property is same, but at this point you have property E1, but here it is E2, E2, E2. So if you have, but we assumed like in every derivation we have Hooke's law or superposition, we said that material is isotropic plus homogeneous. So that means at each point property has to be same in each and every direction throughout the material. Everywhere is same throughout the material. Now if we have orthotropic material, orthotropic material means in the orthogonal directions your property differs. Say in your property in Z is Ez, in the Ex is Ex, and in the X direction it is Ex. So your property in each direction, where in normal perpendicular directions, property in perpendicular directions change. Let's say for example you have graphite, you have wood, you have plywood. Now next one is your anisotropic. Each material in the world is anisotropic in the world is anisotropic, but for analysis we say the material is isotropic. So your anisotropic means in E varies, your property changes at a point with change in direction. E varies with, E means property, we can write as property varies with change in direction. This is your point. Here is property P1, P2, P3, and so on. Now we have the elastic constants. We say that we say that Young's modulus equals to normal stress by normal strain. This one, normal strain, and your modulus of rigidity, that's equals to shear stress by shear strain. And similarly you have bulk modulus of elasticity, that equals to volumetric stress by volumetric strain. But the volumetric stress has to be sigma in all directions. That is sigma x has to be equals to sigma y has to be equals to sigma z. Then only that we can say bulk metals property equals sigma volumetric by volumetric strain. Say it can be hydrostatic compression, or it can be hydrostatic tension. So you have water molecule, then all in all directions you're having force equals to P, that's compressive force. So that is what we call as hydrostatic compression. So we also know that your volumetric strain, equals to sigma x plus sigma y plus sigma z upon E1 minus 2 mu. So if we substitute the value of volumetric strain here, we can get sigma volumetric, we can keep at sigma and divided by k. And we know that for volumetric strain, sigma x equals to sigma y equals to sigma z equals sigma. So we can have 3 times sigma 1 minus 2 mu divided by E equals to sigma by k. Then we have your relation becomes E equals to 3k 1 minus 2 mu. Similarly, next relation is your E equals to 2g 1 minus 1 plus mu. So if you want to calculate the value of k, we say that if mu is your 0.5, we can get the value of k equals to E equals to 3k 1 minus 2 into 0.5, that's your 0. That means k is your E by 3 into 0, that's your infinite. That means it is incompressible fluid. There is no volume change. We know that this is change in pressure, change in volume with change in pressure. We know that your bulk modulus of elasticity is volumetric stress by volumetric strain. Strain is your change in volume by original volume. Since for incompressible fluid, if the volume change is 0, that means your bulk modulus is infinite. That means you're having that's what incompressible fluid means. That means your k equals to infinite. Now if the value of mu comes out to be 0, let's take the value of mu equals to 0. We would say equals 3k 1 minus 2 into 0. That means k equals to E by 3. That's k minimum. Minimum value of k is at mu equals to 0. That's when material is cork. Then k minimum is E by 3. And the maximum value of k equals to infinite. Now, if we want to calculate the value of mu from these two relations in terms of EGK, can we do it? We can say 3k 1 minus 2 mu equals to 2g 1 plus mu. This is your 1 minus 2 mu. We can say 3k minus 6k mu equals 2g plus 2 mu g. Then we have mu 2g plus 6k equals to 3k minus 2g. So your mu becomes 3k minus 2g, 6k plus 2g, 6k plus g, 6k plus g just check it, verified. Actually, we know, see, we know the value E equals 3k 1 minus 2 mu equals 2g 1 plus mu. So it's 3k minus 6k mu 2g plus 2 mu g. So your relation becomes mu 2g plus 6k mu equals to 3k minus 2g. So your result becomes 3k minus 2g by 6k plus 2g. 3k minus 2g, 6k plus 2g. Yeah. Also, if you want to calculate E in terms of k and j, so if you write, we know E equals 3k 1 minus 2 mu. How can we get the value of k? That's if we eliminate the value of mu, from any of these equations, say E equals to 2g plus 2 mu g. So your mu becomes E minus 2g by 2g. E minus 2g by 2g. So if you substitute the value of mu in the first one, you write E equals to 3k minus 3 minus 6k. Your mu is E minus 2g by 2g. Then you simplify, you get 3k minus 6k E minus plus 12k g by 2k by 2g into you multiply here, it becomes 6 kg your E, then it becomes 2ge. So your finally E becomes 9 kg by 3k plus g. You don't have to remember these two, but these two are important. This one and this one is important, rest you can calculate. What should be the maximum value of mu? What should be the maximum value of mu? Maximum value of Poisson ratio, we know, equals 3k 1 minus 2 mu. Let's say it's E by 3k equals 1 minus 2 mu, which implies E by 3k minus 1 equals to 2 mu. Say this part, it's always a factor that's it's always greater than 0, which implies 1 minus 2 mu. This part, we know E by 3k is always greater than 0, so this is always greater than 0, so mu this part is greater than 0 always. So your 1 minus 2 mu has to be less than 0, so your mu has to be less than or equal to 0. So the maximum value of mu is that 0.5. So now we have for the isotropic material, isotropic homogeneous material, we say that we need only two independent elastic constants to define the state of stress. Say if you know E and if you know G, you can get the value of others like K, or if you know E and K, You can get the other values. From that you can get the value of stresses, strains, volumetric strains, shear strains, shear stresses, volumetric stresses, etc. So to define the state of stress at a point, so you need to only you have only two independent elastic constants. Once you got those two independent elastic constants, you can define the state of stress. But for the we have orthotropic material. Orthotropic material. Your property varies in perpendicular directions. So normal stress, your normal strain does not depend on shear strain. Does not depend on shear strain. If it does not shear strain, then we have the equation that strain in x equals to sigma x by E minus mu sigma y upon E minus mu sigma z upon E. But for the orthotropic material, property in x is Ex, property in y is Ey, property in z is Ez. So your Ex becomes sigma x by Ex minus mu x mu y sigma y by Ey minus mu this one is related to a particular plane. We can say mu xy, and this one is for mu xz sigma z upon Ez. Similarly, then if you have the then matrix, if you have the matrix of all this, we can have Ex, Ey, Ez. You have shear strain gamma xy, you have gamma yx, and you have gamma zx. If you represent it in terms of matrix, this is a matrix of 6 cross 1. It has to be equals to, in terms of we can say in terms of some factor into your stresses. Say here it is sigma x, sigma y, sigma z, and you have tau xy, tau yx, tau xy, tau yz, and tau zx. This is also 6 cross 1. Then this one has to be 6 cross 6. So your normal strains does not depend on shear strains. So your the effect of shear strains in these three would be 0. This, and you already know that sigma Ex equals to sigma x by Ex, but sigma x is already there outside, so we can say 1 by Ex and minus mu xy by Ey, and similarly third one is your minus mu xz by Ez. Similarly you can have for all of these three. So you have similarly you have here something. Similarly something. You have 0 0 0 0 0 0. Then you have from this side 0 0 0 0 0 0 0 0 0, and you have shear strain. Shear strain here we know shear strain equals to for this particular plane gamma xy equals to shear stress in xy and divided by g. So we can write, but the property is varying in the particular normal in the perpendicular directions. We can write say gxy. Then we have, so we can write for the shear strain gamma xy we can have 1 by gxy. Similarly for the shear strain yz we can have 1 by g yz, and for the zx we can have 1 by g zx. Then we have 0 0 0 0 0 0. So if you have but the thing is that since the matrices are symmetric about the main diagonal, then we have because of the complementary shear stresses and those concepts, we know that the matrices are symmetric about the main diagonal. So your this part and this part are same, this part and this part are same, this part and this part are same, this part and here is this part are same. So there were only how much these, we can say, these to define the state of stress, how much unknowns you have to define, how much constants you have to define. These 30, actually there are 6 cross 6, that means 36 constants. Out of that, in the orthotropic material, normal strain does not depend on shear strain, so these values are 0 0 0 0 0 0, that are 18. 18 are already 0. Then the remaining 18, out of that you have uh, how much which are independent. So if we count, we say that this is 1, and this and this are same, 1 2 3, and we have 4 5 6 7 8 9. So your total independents are 18. 18 minus your independents are independent constants are 18 were total, which were having non-zero values, minus out of that you have we can say it this way also. Out of that 18, 6 are like in the main diagonal, plus the remaining 18 minus 6. Out of that only, if we divide it 2, so we can get independent these constants because of this symmetry. That's why we divided it by 2, so we can have 9 independent elastic constants for orthotropic material. Similarly, for the, we can have anisotropic material. For the anisotropic material, your normal strain depends on shear strain also. So your matrix looks like, then you have E x E y E z, gamma xy, gamma yz, and gamma zx. This is just extra details. You just need to remember the, like the values of those constants, how much constants are independent. So you have, say here is some constant b c d e f g h i j k l x y z, alpha beta gamma, anything up to, say, these are 6 cross 6. That means our total were 36. Out of that, by the symmetry of the this matrix, we can say B equals G, F equals that zeta. Then here we have this one. That means only 6 are in the main diagonal. In the main diagonal, there are only 6. We can say out of that 36, we have 6 plus 36 minus 6 by 2. This is equals to 21 independent elastic constants. Independent elastic constants are required. That means you have to find the 21 independent elastic constants in order to define the state of stress in the anisotropic material. So it would be hell lot of calculation if you not assume that material is your isotropic, because in your material you say that E is same in all directions. Otherwise you would be facing very much problems. So we said that material is isotropic. So to avoid your calculations from 21 to only 2 when you said isotropic and homogeneous. Now we have a question on, say, the cube. That's, you have a cube element, say any metal or any member. That's the cube is fixed in x and y, but it is free in z. So you have y z x. So it's fixed in x. So the change in length in x would be 0. It's fixed in x. So this is x fixed, and in the y it's also fixed. So only in the z it can move. So deformations would be only in the z direction. Let's say now if the temperature is increased by delta T, say T degree has been increased, delta T increased temperature. Okay, now we need to calculate the thermal stresses. We need to calculate the thermal stresses. We need to calculate the thermal stresses, and you calculate the change in length in z. So we can say it's a cube of size side A. So we can have that if cube is fixed in x and y, we can say strain in x and strain in y has to be equals to 0. So let's say temperature has increased, so there would be stresses developed opposite to that in the x and y direction. Say sigma x has been developed in this direction, and sigma y is also compressive. So we can say that sigma x is, and if the cube is free in z, we can say sigma z is 0, because there is no one to restrain that deformation because of the temperature increase. So your strain in x, we can say it is sigma x upon E minus mu, sigma y upon E, but your sigma x is actually minus sigma times, and sigma y is your minus mu sigma y equals to 0. So we can get value of sigma y in terms of sigma x. So your sigma x, so your no, that see, we got the strain value, we got the value of strain. Now if you want to calculate the strain in x, change in length in x, I can say strain might be there. We can say change in length in x equals to change in length in y equals to 0. If you want to calculate the change in length in x, that's equals to strain in x into your side, that is A. So if you calculate, that has to be equals to 0. We can say that minus sigma x by E plus mu sigma y upon E equals to 0. So that means your sigma x equals to mu sigma y. Oh, I lost the important part of this question. It was missing from my mind. See that the strain because of these two stresses, if you want to calculate separately, we can say the strain has to be 0. But because the material is expanding, we can say that the change in length in x has to be equals to 0. If the material has expanded by alpha a t, it has to be resisted by I would say let's say this has been expanded by this one, and firstly we want to calculate the strain. In x. I can calculate the strain in x, that is sigma x upon E plus mu minus mu sigma y upon E. So your I can say your I can add this one also. So your change because of these stresses, I can say that that's equals to delta dash in x equals to a into ex. Yeah, I would say a into ex. Your ex equals to minus sigma x upon E plus mu sigma y upon E, that equals to 0. If that equals to 0, we can calculate the value of sigma x. But the thing is, let's say for the force equilibrium sigma x, let's say for the force equilibrium there had been some resistance here, P and P. If you divide by cross section, if you divide the load by cross section, that is a square, that comes out to be sigma x. Similarly, but the cross section at the top is also a, because it is a cube, so your sigma y and sigma x are same. Let's take the value of sigma x and sigma y equals to sigma. We can say a t plus a minus sigma plus mu sigma by E equals to 0. Then we can have let's say alpha t plus minus minus sigma 1 plus mu, no, 1 minus mu divided by E equals to 0. We can say that sigma equals to EAT 1 minus mu. This is your result, that thermal stress, that thermal stresses developed in x and y direction are equals to EAT by 1 minus mu. Now if you want to calculate that strain in Z, we know strain in Z is sigma Z upon E minus mu sigma x upon E minus mu sigma y upon E. Your stress in Z is 0 minus mu. We can keep the common, we can take the mu and E common, and minus also, so we write, and sigma x and sigma y is also same, so we can say this is your minus twice times mu E by sigma. Sigma x and sigma y is your sigma thermal, that's E by 1 minus mu. Okay, you got the value of strain in Z equals to minus 2 AT mu upon 1 minus mu, but it comes out to be negative. Yeah. One thing is there, that the sigma x and sigma y were compressive, so that the overall value comes out to be positive, because the length in the Z would increase. So your change in length in Z comes out to be equals to strain in Z into side in the Z, that is equals to A, that is twice A alpha AT mu upon 1 minus mu. Do we got this value? Oh, one thing, this part we have calculated that strain in Z because of the loadings are, that's equals to the, 2 alpha t mu upon 1 minus mu. That's because of the effect of stresses, but the material is also increased, subjected to temperature rise, so that the material is also expanding. So delta Z, because of free expansion, is also there. Free expansion, that is equals to alpha AT. Then if you do the total delta change in Z, that equals to 2 alpha AT mu upon 1 minus mu plus alpha AT. Then you do calculate it, you get the value of, if you solve it, solving one more step, you can say twice alpha AT mu plus alpha AT 1 minus alpha AT mu divided by 1 minus mu. So we can get 1 plus mu 1 minus mu alpha AT. That's your change in length in Z. Now same question, But the thing is, we don't we don't want the z to be free. We keep all the sides as fixed. Let's keep all the sides fixed. Let's say all the sides are fixed. Let's say all sides are fixed. Cube side A, temperature rise by T. So you have this one. So if the sides are free, so that then the thermal stresses would be developed in each direction equals to sigma x. So your sigma x equals to sigma y equals to sigma z, because all sides are equal, because area is same, and for force equilibrium there is no external force. So P in the x equals to, say, force in this x direction has to be equals to force in this direction, say P, and each direction force is equal, because each side material is expanding alpha lt. So your force is also resisting that delta which has occurred. So your P in each direction is also same. So your sigma x equals to sigma, I can write as in this direction also sigma compressive. So we have the result that strain in x, we had the result that we can calculate the strain in x, that strain in x equals to minus sigma by E minus mu, sigma by E minus mu, sigma by E. And similarly we have that's also equals to sigma y, yeah, that's also equals to strain in y, that's also equals to strain in z. Now we have to calculate the value of sigma. We can say we say that the total deformation in x equals to total deformation in y equals to total deformation in z, that's equals to 0. This is your compatibility condition. So if you add all those, so let's say strain in x is ex, because of those reactions. We can say the delta L in x because of those reactions, that's equals to strain in x into side A, exa. Now we have we can say delta change in L, change in length in x direction equals to 0, then which implies that strain in x into A plus alpha at goes to 0. Then we have strain in x equals to minus sigma by E minus mu sigma by E minus mu minus sigma by E plus alpha at equals to 0. Then we have the value of stress that comes out to be equals to EAT by 1 minus 2 mu. This value we can also solve by volumetric strain. We have volumetric strain equals to sigma x plus sigma y plus sigma z. This volumetric strain equals to Ex plus Ey plus Ez, that equals to sigma x plus sigma y plus sigma z upon E 1 minus 2 mu. Okay. We know that strain in x equals to change in length in x divided by original length in x was A, divided by change in length in y, change in length in y divided by original length in y was A, change in length in z divided by original length in z equals to 0, and sigma x equals to sigma y equals to sigma z. That means 3 times sigma divided by E 1 minus 2 mu. Then we have that I would say that your volumetric strain is change in volume by original volume is your A cube No, for volumetric strain, for change in volume to be zero, we can calculate. We can say that uh, your change in length in x, say delta Lx is your alpha lt plus alpha lt divided by a divided by a divided by a, that equals to 3 sigma by E1 minus 2 mu. We can say 3 times alpha, L is your A, so we can say 3 times alpha T equals to 3 times sigma by E1 minus 2 mu. So we can say sigma thermal equals to EAT Y1 minus 2 mu. So if you have now the mathematical definition of strain, mathematical definition of strain, we say that the, let's you have direction y, you have direction z, you have direction x, you have a body, say take a point P whose coordinates are x, y, z. Then if u, v, w are displacements in x, y, and z because of forces you applied and moments on the body, then we can say that your strain in x is your change in your displacement u, dou u by, with respect to change in x, dou u by dou x. Strain in y equals to dou v by dou y. Strain in z goes to dou w by dou z. Similarly, shear strain gamma xy goes to dou u by dou y plus dou v by dou x, and dou xy, and dou, you can say dou zx goes to dou w by dou x plus dou u by dou z. Similarly, dou xy goes to dou yz equals to dou yx equals to dou v by dou z plus dou w by dou y. The last topic is your Boss-Singer effect. Say you have a mild steel specimen. You applied, now you got a stress strain curve as this way. Say this is your elastic limit, this was your proportional limit A, and this is your elastic limit B. Let's say you are loading till at the rate of that stress. If stress exceeds that sigma B, if the stress is greater than elastic limit, then that after that plastic deformation would happen, and if you reload, the path followed would be such that, let's say at this point you are unloading. This was your loading diagram. If you are unloading, the path followed would be this way, such that it is tangent to the, such that it is parallel to the initial portion of the curve. If it is tangent here, so it cuts here. Now this part, now this is your now I can say this is your new yield strength. Initially we were saying sigma b is your yield strength or sigma d is your yield strength. Now point has been changed to the other point, and because of that, if you now load it in reverse direction, and if you get the stress strain curve in, say, in the compression, new curve would be formed that is like this. So your sigma y in compression has been decreased as you if you load the if you load the specimen at stress greater than sigma b, say elastic limit in the tension. If you applied stress load such that the stress, if you applied the load such that the stress in the tension zone comes out to be greater than elastic limit, then upon unloading, the path followed would be this one. And if you then reverse the loading, say in the compression, the curve would be this one. There is a decrease in strength in the compression. That's called as Bose-Ginger effect. Hope you enjoyed the first chapter of your strength of material. This was all related to stresses, strains, deformable bodies, and the stresses calculation based on deformation of bars, and next one was your thermal stresses. Hope you enjoyed the video.